questions about how to solve certain things, I will not answer those because, yeah, it's not. I mean, I could. Yeah, it's not part of my work. So I teach here, and then, but there should be some channel for you to come and ask questions. I mean, usually we do that in the break at 9, but now since we're having online classes, there is no such break. But well, today there is no such break. But try to take your questions, whatever questions you have, and then, I mean, either you direct them to Daniele, who is excellent in explaining how to solve things, or we can actually do them in the break, which we won't have one today, but in general there should be a break between 9 and 9:15. So then we can solve it by discussing here in the forum. So I was also thinking of maybe setting up some doodle schedule whereby some of you could come here and listen to the class, like just a few every time, and one could sign up. I don't know, is that something you would want, or is it fine like this with the online classes? What do you say?
I would like going for the
Right. Okay, so I'll try to work that out. It has to be some system that very few people, you know, come and not, but probably some doodle or something. Okay, good. So much about that. So let's get this class running. Last time I told you to read a bit on your own because it was basically repetition of definitions, or very just similar definitions as what we have in analysis 1 about what's a, you know, supremum, what's an infimum, what's a sequence, and so on. Where's my screen share? All right, so I hope you can see the lecture notes. Right, so we have sequences, and they can be infinite, and okay, there's a least upper bound, greatest lower bound. That's just a different word for supremum, infimum. And then we have this theorem, which is not really in the book, that we're going to prove today, which is using some very nice tools. So this is more like, if you take the course functional analysis, it will continue in this direction of showing how to work with sequences. So a continuous real valued function on a compact set K assumes a maximum and a minimum. And okay, now I'm going to use the blackboard. To see why we need a compact set, I'm going to do an example, and I'm also, with the example, we're going to see the road forward to actually proving such a theorem. Let me do the camera. I see the camera goes in and out of focus as usual, so escape. And then wait, okay, so the focus should be. Okay, so now the focus should be fixed. So just take a function. So here's 0. There is 1, and look at the function y equals to x, yeah? On this interval. So the supremum doesn't exist, right? Because we know that the supremum of all the values here is equal to 1, right? But since I didn't include the right end point, it never assumes 1 on this domain of definition. Yeah. So if instead we make it inclusive so that 1 and 0 are inside, so closed intervals we denote like this, then yeah, then the function assumes its maximum at the point 1, it is equal to 1, which is the maximum value. So we have that f, well, yeah, if we call the function f, then we have f of x, well, I just write x then. So x is less than 1, no, okay. Okay, so x equal to f of x is less than or equal to 1, which is equal to f of 1. Yeah, so you find a point in the domain such that the function value there is bigger than all other function values. This is what it means to attain its maximum, and we're looking for such points, right? In this theorem, it says that there always exist such points. And to see what complications can arise, let's instead take the function modulus x from -1 to 1. Yeah? So now the function still attains its maximum. It's just that there are 2 different points where this happens. This is not a problem. It's not in contradiction to the theorem of Weierstrass, which just says that 1 point exists. But it is a complication in the proof, because how could we go on about proving such a thing? Well, so the supremum exists, right? So there is some roof to the function values you can have. And this means that we don't know that the supremum is attained, but we know that we can get arbitrarily close to it. So in this case, the supremum is 1. So I know that if I can find some value, which is about, let's say, 0.99, and then I pick a value like that, maybe this one. Yeah? Or let's start a bit further away. So we start with 0.9. Okay, so I pick this guy. Now let's say it's bigger than 0.9. Then I pick another one where it's bigger than 0.99. But that one may be over here. And then I pick a third one, which is bigger than 0.999, which may be over here. And like that, I can fill up, again, a sequence of points where the function value gets closer and closer and closer to the supremum. Now, the idea here, or what we want to do, is then to say that, well, this sequence has a limit, and the limit point is the one we're looking for, right? And this is where continuity comes in. So we need continuity of the function f. The problem which you see here on the blackboard is that there may not exist a limit, because the sequence it bounces back and forth. However, it's clear that if we just focus in on the part of the sequence that's close to the right endpoint, or to the left endpoint for that matter, we just make a pick, then that subsequence will converge. So this leads to interesting questions of the form, if I just have a sequence, can I find always a convergent subsequence? So these type of questions are studied in depth in functional analysis. And here we're going to just touch this a bit on the surface. And the answer is yes. So if you have a bounded sequence, you can always find a convergent subsequence. And this is the lemma, which is coming up in the lecture notes here. But let me first mention two things that are at play here. So the first is, what do we mean by a sequence to be convergent, right? Because now we're in several variables. This example was one, but in the lecture notes we're in several variables. So let me write up here a definition. A sequence, okay, let's call the sequence something. So xn, n goes from 1 to infinity. This is a notation we use for, instead of writing x1, x2, x3, comma, dot, dot, dot. This is a more short notation, right? So this is to be read, you have xn, n starting at 1, and then going through 2, 3, 4, 5, 6, up to infinity. So this is a notation for sequences. It's convergent, and then we need some convergence point, let's call it y, if. So you remember the definition from Analysys 1. So if these were not vectors, so this is a sequence of, of vectors, of points in R2 or Rn. If we just had numbers, then what we would have wanted is that xn, okay, I write over here, you see it's still right. So xn minus y is less than, oh, well. I have to introduce first my epsilon. It's convergent to y if for all epsilon bigger than 0, there exists an n, which is a natural number, such that xn minus y is less than epsilon for all n bigger than or equal to big N, right? This was our definition in the one variable setting. Meaning basically, okay, so if this is the real line, here's the number y. So to say that something xn minus y is less than epsilon is to say that it stays inside a small interval centered at y. So this thing with the big N here just says that, well, maybe this sequence starts over here and is very far from y in the beginning, but at some point when n gets big enough, you go inside this little interval and then it stays there, okay? So for all n above that point, it stays inside here. So all of these n are close to y. And then we can do this for an interval of any size. So even if I make this interval much, right? So this is the idea of convergence of a sequence. So you can compare with convergence of functions or limit of functions that we did the other day. It's very similar, right? You pick an epsilon and then you make sure that the values you're interested in are within epsilon of the limit x. You're close enough to the limit point you're interested in, right? So in this case, N goes to infinity.
We cannot see you. The screen froze.
Oh, since how long?
Just 1 minute or less.
Right. Just wait a bit and see. Did the picture come back?
No.
God damn it. All right, can you see me now? Or is it still frozen?
It is still frozen.
Oh, god damn it. Okay, I'll just turn down the entire Zoom and restart it, okay? Hello, can anyone see me now?
Yeah, you're back now.
All right. Um, okay, so where was I? Well, I was saying that all this, the idea of a limit, once you get the hang of it, they're all of them similar. So you pick an epsilon, and then you always want some other condition that either n is big enough or your point is within delta of the limit point. Whatever you want to be fulfilled in the type of limit you're looking at, you should have that. So you pick an epsilon, and then comes some condition, in this case n bigger than n. All right, so this is for one variable. Now, how would we do this in several variables? So now, as opposed to an interval, we have some domain, we have a point y, and we have a bunch x1, x2, x3, and so on, of points approaching y. Well, what do we want? We want then, of course, that the distance between xn and y is less than epsilon for all n bigger than n. So it's almost word by word the same, right? And the idea is the same as well. You just, the picture looks a bit different. So now this condition here, xn minus y less than epsilon, you can think of it as having a small disk, yeah, inside your domain around y. Just like here we have an interval around y. now we get a disk. And the point is that, okay, these x1, x2, so on, they can be outside. But sooner or later, when n is big enough, they go inside. So that's what it is to have a limit in several variables. And now, the second thing you need to know about continuity and sequences before we move on is the following theorem, which goes through word by word identically as in the Analysis 1 course, which says that a function f on, well, okay. On a compact set in Rn is continuous if and only if limit as n goes to infinity f of xn is equal to f of the limit xn as n goes to infinity for all convergent sequences. Yeah, so this theorem should be familiar to you in the one variable setting, and the proof and the statement is exactly the same in several variables. This thing that f lives on a compact set is not really relevant. You could reformulate this as a pointwise statement. So f is continuous at the point x0 if and only if you can interchange limits like that, where the convergence point of the sequence is x0. But the bottom line is continuity, and being able to swap limits from outside to inside is equivalent. Yeah?
What is exactly meant by compact set?
This is closed and bounded.
Right.
But again, that's not the key part of this. The point is you have a function f is continuous if and only if you're allowed to do this. I want the set to be compact just so that the limit point actually exists inside the set. So actually, yeah, probably close this enough. Okay, so with those two ingredients, we go ahead and look at the lemma. So I'm going to share screen with you again. Okay, so here is the definition of convergence, which I wrote on the blackboard. Okay, so here we come to this. I have a problem moving up and down in my script here. All right, So lemma 1, a bounded sequence of points in Rn has at least one convergent subsequence. And the proof here is very clever. So even in one variable, I don't know if you had this as part of your Analysys 1 course, but anyways, we're going to do the proof here, because once you have the proof for one variable, you can actually mimic the proof of several variables. So what's the idea? Okay, so again, here's the real line. And you have a bunch of points. Maybe one here, one there, one there, one there, one there, one there. And they don't converge really to something. But if you have infinitely many of them, and they all stay within some, upper and lower bound, so this could be, I don't know, a to minus a. If I keep filling up here, of course I can make it so it doesn't converge, but it's going to have some accumulation point, right? Some point where there are just more and more of them. And if we look at that point, then that should intuitively be, a limit point. Question is, how do we find it? So if this interval is called I0, yeah? What I can do now is I split this one in two. So I put the divider here. Now, three things can happen. Either I have infinitely many points here, or I have infinitely many points here, or I have infinitely many points in both. Yeah? So I can always pick one of these two intervals where there are still infinitely many points. Let's say okay, actually I said this interval was minus a to a, but I want it to be a to b. Okay, and then, so now we pick I1, let's say this one, so that it has infinitely many points. And then we do this again. So I cut this one in two. So either there are infinitely many points here or there. So let's say now it's on the left one. Then let's call this one I3, and so on. I cut this again. And here will be my I4. Yeah? So now you see what's going on, right? So I get smaller and smaller intervals, and they always have infinitely many points in them. So somehow intuitively, these intervals should narrow down on one single point, and there should be some sort of subsequence converging to that point, because there's always, infinitely many points in my sequence around that guy. So okay, but that's intuition. How do we extract it mathematically? So mathematically, what we do know is that if we have an increasing sequence, then it has a limit point. And that's closely connected to the least upper bound axiom. I think it's even equivalent to the least upper bound, or the completeness axiom of the real line. So, all right. So I0 is on interval A0 to B0. Yeah. I1 is another interval, A1 to B1, we can call it, where either A1 is equal to A0 or B1 is equal to B0. Yes, now I'm just going to relabel this one. I put a small 0 here. So in our case, B1 and B0 is the same. but A1 is bigger than A0, right? And then I continue like this. So I2, I'm going to label it A2, comma B2, and so on. Yeah? Now, what we have here is that A1 is less than or equal to A2, is less than or equal to A3, and so on. Similarly, B1 is bigger than or equal to B2, bigger than or equal to B3, and so on.
Question.
Yeah.
So you do relabel what basically where B0 is in I0 becomes B1, and then it, yeah, okay, good, thank you.
Right, so this is an increasing sequence, and it's clearly bounded from above by B0. So by the completeness axiom of the real line, the limit exists. And this limit, we can call it what? We can call it y, okay? And here, I leave some details that I'm trying to explain the idea. The details are well written up in the manuscript, in the lecture notes, so I'm not going to write everything out. But for each, the length of these intervals go to 0, right? So by that alone, it's easy to see that the limit of the bn's also exists and is equal to the same thing. Or if you want, you can say that this is a decreasing sequence, so it has also a limit. But since the distance between an and bn goes to 0, the limit of this sequence must be equal to the limit of this sequence. So both of them have limit y. So I just write it is easy to see that also limit of bn is equal to y. Okay, so now we have some point here y. And we kind of feel that is the point we're looking for, but we still don't have this subsequence. Okay, we need a subsequence that converges to this guy. And how we do that is very simple. So in I0, well, it has all of the points of the sequence. So we can always pick some point here. So let's pick x1, for example, in I0. Okay. Then for the subinterval I1, we do not know if we can pick I2, sorry, x2 in here, because x2 might be over here. Also x3, x4, x5, x6 might be in here. So maybe, you know, we have to wait until 7 before we find a point in here. But there are infinitely many points of our sequence in this interval. So at least we can pick, you know, if we're just patient enough, we can pick one. So let's say we have to wait. So let's say x7 is somewhere here. This guy is x7. Then we can pick x7 in I1. And then like this, maybe x15 is in I2 and so on, right? So like this, it evolves a subsequence easily by just picking one guy in each of our intervals. So this process of picking gives us the subsequence. And now I'm going to write something you are not going to like. X and K, K going from 1 to infinity. Do you still see what I'm writing there? Well, it's on the edge, yeah? Okay, what is this? X and K. So N, K are now numbers. So in this example here, you would have N1 is equal to 1, N2 equals to 7, N3 equals to 15, and so on, right? So this is X, N, K. So for each K, N, K is a number, the number that we pick at the kth step here. So step 1, pick X1. Step 2, pick X7. Then N2 is equal to 7. Step 3, pick 15. Then N3 is going to be 15, and so on. So this is the notation then for subsequence. Okay. So now to finish up here, we have found our limit point y. We have our subsequence x and k. We just have to prove that it actually converges to y. And how are we going to do this? We do it by the squeeze theory. So note, we have so AK is less than XNK, less than or equal to BK, right? This is just saying that XNK is in the interval IK. And limit AK is equal to y, which is equal to the limit of BK. Well, this is exactly the setting of the squeeze theorem, right? If you can squeeze a sequence between an upper and a lower one, and you know that the upper and the lower one converge to the same thing, then the guy in the middle has to converge to that as well. So y is equal to the limit. Look now, k is the one where we take the limit, right? So this is the subsequence, x and k. As k goes to infinity, this converges to y by the squeeze theory. Okay, so this, at least I find it a beautiful proof. Very, very nice ideas. Am I in the way of the text? No. Okay, so this was for one variable. In several variables, what could we do? I'm gonna move this guy. Okay, so I have a bit of space to write here. Now, so in several variables, of course, let's take two variables. If I have points here and they are bounded, I can, of course, take some big box and put around it. And then instead of choosing a subsequence, I divide my box into 4 compartments and pick one of the 4 compartments with infinitely many points in it and go on like that. And I just mimic this proof all the way through. That's one possible way of doing it. But, okay, so an alternative way is to actually just do induction on what we have here. So we have proved this for one variable, but if you have a sequence of points in 2 variables, it has a first and a second coordinate, which are just one variable sequences, right? So you can actually use this lemma on the first coordinate to get a subsequence that converges, and then use it on the second coordinate and get a subsequence that converges. So let's look at that argument. So now let xn be a sequence in R2. So what this means is actually now I have well, so how do we write this out? I have pairs, right? So x1, x2. This is my first. But you see now I get into a collision of notation because so the vector x1, it has the first and the second coordinate. So how can I call this? Well, actually, this is x1, then first coordinate, and x1 second coordinate. So it looks like this. x2 has two coordinates, so it's x2 first coordinate and x2 second coordinate, and so on, right? So formally, we have that, you know, x n bar n goes from 1 to infinity is the same as, well, written out more, it's xn comma 1 comma, big comma here, and xn comma 2. N goes from 1 to infinity, where xn1 and xn2 are sequences in R. Right? So the first coordinate and the second coordinate is now a sequence that falls into this machinery over here. So I keep using this side of the blackboard here. Okay, so how can we prove that this has a convergent subsequence? This one gets a bit messy notationally. On an ideal level, it's very simple. The problem is here, you know, I can choose some n case, a subsequence such as the first component converges, right? And I can choose some n case such as the second component converges. It's just that these n case might not be the same, right? I have one subsequence here and one subsequence for this guy. And if they are not the same, then I just get one case where the first coordinate converges and the second coordinate does whatever, or the second coordinate behaves well and the first coordinate is just doing whatever. So I have to be a bit more clever than just going for each coordinate independently. And how do we do that? As follows. So first, so use the one-dimensional result to pick n case, so sub-indices, such that x and k comma 1, k goes from 1 to infinity, converges. Let's say to some number y1. And now you want to consider the second component, but not the second component xn comma 2 with n. No, the second component of the subsequence that we got from the first variable, right? So now I have xnk comma 2. Here, when I pick these guys, I just work with xn1 or xn comma 1, and I get my xnk. Right, so this is a sequence in k, right, of numbers, one dimensional. So since this is a sequence, I can pick a subsequence which is convergent. It's just that now, right, so this idea is not complicated. It's just that now we run into notational difficulties, because what on earth am I going to call that subsequence, right? Well, if we follow the notational machinery, here's a sequence in K. So a subsequence of that would be, I pick numbers K1, K2, K3, and so on, right? So let's do that. So K1, K2, and so on. How can I call it? Km. M equals to 1, 2, 3, dot, dot, dot. Such that, so now we have X, N, K, M. Look, this starts to get really ugly. We have now 3 sub-indices here. Comma 2, as M goes from 1 to infinity, converges to some number, let's call it Y2. Then this is easy. So what do we have? We have that X, N, K, M. As M goes from 1 to infinity, now the vector sequence, so the containing the first and the second coordinate, converges to the point y1 comma y2. That we're going to call it y. Why is this? Because the sequence I wrote there, x, n, k, m, it has a first coordinate which runs through a subsequence of the subsequence that was known to converge. So a subsequence of a convergent sequence, that's still convergent, right? And the second coordinate, it converges because we chose the subsequence nkm so that it converges. So now we have a first component that converges, we have a second component that converges, and yeah, then the object in R2 also converges, right? Convergence in Rn is the same as having each component converging independently. So yeah, that's the idea of the sort of lifting process, which you find here. Okay, so now there's a question. Heine Borel, so the names of theorems, I don't know this very well. I got a bit not so interested in it after a while, because these theorems are always named after someone else than the person who actually did it. That's the first thing. And then it's like, I don't know, different people invented the same theorem, but there's like some post-construction that, yeah, but if it's in this setting, we call it Heine Borel, and if it's in the other setting, but there's also Helly's selection theorem, and they all say the same, but in various settings, right? So yeah, if this one is called Boltzmann or Heine Borel, I don't know, but Probably Heine-Borel. And then Helly's selection theorem is probably some infinite dimensional version of that. Yeah, so you go into Hilbert spaces. But you know, this is there's a theorem in math that there is no, well, it's like a funny theorem, that there is no theorem was actually named by the guy who cooked up the proof. So yeah, I was like Boltzmann, what? But okay, Bolzanos. You caught me there, eh? So whether it's Bolzanos or Heine-Borel, I don't know. Maybe there is a Boltzmann who. What, L'Hôpital? What does L'Hôpital got to do with this? Ah, okay, you wrote something about that. Anyways, you people slow me down with this discussion. Let's get back to the topic. So, all right, here's the division process that I went through. And now, right, now he does it in 2 dimensions. And he also gets into this. You see here this ugly notation, YKJL. So it's exactly what I had here, just I call it NKM. But so same idea. So then hopefully, I mean, yeah, hopefully you find it easier to read these proofs after listening to me here. Okay, so then let's do the proof of Weierstrass theorem. Or do you guys want a break? No, let's do the proof of, what do you say? Should we have a quick break? Or, yeah, let's do that. I run for coffee, you freshen up your brains a bit if you got tired. This is a bit heavy on the proof side, so try to think about what this lemma said and then freshen your brain and remember what Weierstrass theorem is about and how you would possibly prove it. Right, and I'll be back in 5 minutes and show you the details of how to do it. so I am back. All right, so why did we get into all of this business with the subsequences? Well, it started from a very simple idea that we have here on this screen, right? So if I have a function which is continuous, I can pick points that get closer and closer to the supremum value. But like in this picture, they could be divided into different some of subsequences or groups that converge to different things. Intuitively, it's clear that this guy's converge to 1, this guys over there converge to -1, and that's what I formalized with this lemma, right? So now we know in the multivariable setting that given any sequence of points, as long as you're in as this sequence is bounded, it has a subsequence that converges to something, a number y, right? So why do we work in several variables with compact sets? So closed and bounded. Well, bounded, because otherwise we can't use the lemma, right? We need a bounded sequences. So then the domain where the function lives need to be bounded. Why do we work with closed? Because, well, the lemma says that you can pick a subsequence that converges to some y. But if the domain is not closed, that y might be outside the domain of definition of our function. And then we got nothing, because then the function value doesn't exist at that point. So closed means, remember, right? So closed means you contain your own boundary. That's an equivalent definition of closed. So sets that contain their boundary points are closed. So a closed set, we know that if you start with a sequence, you can find a convergent subsequence, and since the set is closed, the convergence point is inside your set. And then things are pretty easy, yeah? So what's the idea here of the proof? I will just erase the blackboard. Right, so how does this look? We have our closed and bounded set, or x1, x2 direction maybe. And here's the c direction, and then we have the function values, a graph sitting on top here. And we're looking for, this point, this is the maximum value here it can take, m. So, and this sits above some point y. And we just need to find that point y. How could we go on about doing this? So, well, so we start here. So m is equal to the supremum of the function f of x, where x takes all possible values O. In our domain, which I didn't give it a name yet, let's call it D. So this set down here in the x1, x2 plane is called D.
You are slightly unfocused. It might not be that big of a problem if you can fix it, but just...
No, I can fix it. Let's go out of the screen sharing, because anyways I'm gonna talk for quite some time. So I don't know if this camera, if I get out of picture, hopefully it should.
Maybe it's just as focused as it can be.
Yeah. Well, that's annoying because, I mean, it's a good camera, so it should be. Well,
fine like this.
Sorry?
It's fine like this.
Yeah, I think that's the best as it gets. Okay. So what would be the idea here? Okay, we don't know that there exists a point that takes this value m, but since this is the supremum of all possible values, if I just go a little bit below m, I can always pick a point that takes that value, or at least above it. So then you would do like pick x1 such that f of x1 is bigger than or equal to m minus 1, right? If no such point exists, then the supremum is less than m minus 1 or equal to m minus 1. So there must exist at least one such point, right? And then you pick x2 such that f of x2 is bigger than or equal to m minus a half. And then we do this at the kth step. You pick an xk such that f of xk is bigger than or equal to m minus 1 over k. Right? So now we got our sequence here, and the way this surface look is going to close in on y because there's only one maximum. But we could, of course, imagine a situation. Actually, maybe my picture wasn't very well painted here. Maybe the surface goes up, and there are actually another point here with exactly the same value. Then we could get into this situation that, well, some of the xk's are around here, and another bunch of xk's are over in this corner, right? And that's why we need the lemma, which says we can take a subsequence so that we have convergence. So now use lemma to pick subsequence x and k. K goes from 1 to infinity. Oh, well. Yeah, I usually number the first sequence by n. So let's have here n instead of k. Doesn't matter. Because now the notation x and k becomes natural for the subsequence. So we pick a subsequence that converges. So x and k should have limit point y. And basically then by continuity of f, so we can have limit of f, x, and k as k goes to infinity. So f is continuous. I can move this limit inside. Sorry. So then I get f of limit x and k, which is the same as f of y. And this I claim it's equal to m. Why does the limit need to be equal to m? Again, this is the squeeze theorem, because actually we don't know exactly what these values take. We just have an inequality. So by the squeeze theorem and the observation that m minus 1 over nk is less than fxk less than or equal to m. So the upper side here is just constant. You can think of a constant as a sequence. The limit of a constant sequence is equal to, the value m. And here you have a sequence that increases, right? And the limit of this sequence as a function of k also is going to be m, because nk goes to infinity, right? So this one goes to m, this one goes to m, this guy sits squeezed in between, so the limit here also needs to be m. Yeah, so this limit is m, right. So now we have a point f of y, which equals m. So yeah, pretty straightforward. Now, I don't know if some of you have been peeking in the manuscript, I cheated a bit here. So why is this not a complete proof? Because it is not. Where did I cut corners here? So in mathematics, you're not allowed to assume anything that you don't prove. There's one underlying assumption here, and these are very easy to make by just not thinking about them, right? But the assumption here, which I'm using all the time, is that m is actually a finite number. We have never said that the function is bounded. We just said that the domain is bounded and closed. How do we know that we're not dealing with a function where instead of this graph just continues and goes up to infinity? So this supremum is actually infinity. If my m here is infinity, then I'm dealing with infinity minus 1, infinity minus a half, infinity minus, this just becomes a nonsense argument in that case, right? So the first step here is actually to rule out the possibility of m being infinity. So but the good news is that this is done in exactly the same. So let's say this graph just goes up here. We have a, just shoots up in the sky. Then you say, okay, well, if the supremum is infinity, then I can pick a sequence in this corner here, where the first value is bigger than 1, the second value is bigger than 2, the third function value is bigger than 3, and so on. And then actually we're in a very similar situation. So now we have a bunch of points, fx1, fx2, and so on, that get bigger and bigger and bigger and bigger and approach infinity. Okay, then you use the lemma to pick a subsequence that converges to some point. In this case here, limit point would sit over there, right? And then, but still you're continuous at that limit point y. So you know that this moving in and out of the limit is okay. So on one hand, you have f of y takes a finite value, but that finite value is equal to this limit, which in turn goes to infinity. So that's a contradiction, right? Yeah, so if you look at the manuscript, the lecture notes, the proof starts out with an argument exactly like that, and then it goes into this argument I showed you here. But the two are very similar. So I showed this one since it's a bit more interesting, actually, I find. Okay, so right, so some examples here to wrap this up. It gets a bit nerdy here in the end. I would not worry about this. A continuous function defined on an arbitrary set in D is locally bounded. Okay, but well, who cares? The only interesting thing here is maybe the example. So how can we find I mean, right. So it's hard to find interesting examples really of how to use this theorem because it's an existence theorem, and it says something which is pretty natural, right? Well, actually, we come back to this later in the course when we do optimization. Optimization is how do you find the point where a function attains its maximum. So far, we just proved the maximum exists. So if you want examples of how to find it, then you just have to hold on a bit. So this example here is just saying basically, again, that we need the domain to be closed for these to be true, closed and bounded. So if you look at 1 over norm x minus a, how would we paint that? So it's a bit, this is an example of this phenomenon over here really can happen. Yeah, so if my point A is here, and I look at the function 1 over x minus a in norm, then, okay, so here's the z-axis. It's going to look like this. So it's some sort of inverted ice cream cone that reaches the sky. So this is a function. Okay, we can restrict the tension then to a punctured disk. So we just look at the function values, you know, this piece of it. Then we have a bounded set, but the function does not attain its supremum, and the supremum is actually infinity. And why? Because it's bounded, but it's not closed. It doesn't contain the point A. Why doesn't it contain the point A? Because the function has no value there. Of course, you can go in and say, okay, but I define it at A, so no, the function at A is 15, and outside it is this. Why doesn't it contradict my theorem? Because if I define it to some random value at A, it's not going to be continuous there, right? So the Weierstrass theorem talks about closed bounded sets and continuous functions, so functions that are continuous on every point in that domain. Yes. So the norm is the one, it's always the one you get from Pythagoras theorem, right? So the absolute value, I'm answering a question now if you wonder why there was a sudden shift of focus. So the question is, what's the difference between norm and absolute value? Absolute value, you put that, there's a one variable phenomenon, right? The absolute value of a number is just, if it's negative, you take the positive counterpart. And if it's positive, you do nothing, right? So norm of a number x, it has, okay, well, I need a clean blackboard. So this is the function modulus x, or absolute value of x, right? If x is positive, do nothing. If x is negative, throw away the minus sign. So this exists only in R. In Rn, we can talk about the norm of x, which is equal to square root x1 squared plus x2 squared plus xn squared. This was first lecture. So in one variable, they coincide, but in several variables, we never talk about absolute value. The absolute value is just a one variable thing that happens to be the norm. Why are they the same in one variable? Because if it's just like one variable, so there's just x1 here, then you get x1 squared and then a square root. And it's easy to see that that's doing exactly the same as here, right? If you have a positive number, you square it, and then you take the square root, you get back the same number. If you have a negative number, you lose the minus sign when you square, and then when you take the square root, you get back to the same value, but without the minus. So in two variables, this can actually be painted, and it is like the modulus, the absolute value. It's just that it has this. It takes that shape, but it's like a cone. Yeah. So this is what the norm is. So if you want, the norm is the absolute value, but rotated around the y-axis in the R2 setting. Good. I'm done with what I wanted to say. Again, if you have questions, it's so much easier for me if you ask them in these, pieces that, for example, leftover, minutes at the end of the class, than sending me emails. Because sending me emails, usually, I'm doing research or something, and then I get these emails. I usually don't reply to them, actually, unless there is something serious. But like, how do I solve this exercise, or what can you explain this proof? I'm not going to go into that, because that would just consume all my time. All right, but before you guys log off, I want to say that, so in total of this course, we have 24 classes, that we meet. And the lecture notes are 18, and probably 3 classes is what we need for recap. So in order to not, so there will be some canceled lectures. So the first canceled lecture is the one on Friday. Yeah, and I haven't gotten, let me see if Daniela wrote me. Right, so both lecture and seminar on Friday is canceled. So next time we meet is next Tuesday. And all right, I will try to get a Doodle something running, so that some of you can come here and interact with me in person at 2 meter distance. So I'll work on that. And yeah, that's it. So if you have any questions, I'm here. Can I recap? Okay, here came the first question. Can I recap why m cannot be infinity? So let's to visualize why m cannot be infinity. I mean, technically, I could just argue, well, you know, technically I will prove it, but to visualize it, okay, so here we have a concrete function that goes to infinity at the point A. So let's understand then why this does not contradict our theory. It is because, so okay, if this is my function f, x, and let's say that, you know, I need a closed and bounded set. So f exists let's say all points x such that x minus a is less than or equal to 1. Okay, so that's this disk here with radius 1, and less than or equal to is important, so we get the boundary. Well, now I actually lied, because this number 1 over norm of x minus a, it exists at every point except at a. Yeah? So the function value doesn't exist here. So, but that we can easily fix. You know, I just take that, okay, so this is the definition if x is not equal to a, and if x is equal to a, then we set f of x to be equal to what? We have to choose some number here. Let's say 10. Okay? So now all of a sudden the function has a value, and it's that one. Right? Problem is, with this number or with any other number I pick, I'm not going to get continuity at that point, right? So if I take a sequence of points such that the function values goes to infinity, they're going to close in on my point A. So the limit point is going to be A. But if I want my function to be continuous at A, then it can't go off to infinity here because it has to converge to the value at A. So my graph cannot look like this. It has to look something like this, right? So at some point it goes back down here. So I get a volcano, right? Anything else would violate the continuity condition at the point A. Right? So yeah, I don't know if I got my point across, but the idea is this: you pick points such that you get numbers which are higher and higher and higher. These points will converge to some limit point A, but at that limit point A, the function value is finite. So then these are, you know, if you have continuity at that point, they cannot go off to infinity. I hope that answered your question or gave you some tools to try to understand it. So the next question is, will we be covering Friday's material next Tuesday instead? Yeah, so the lectures in the sheet, the course plan, they're just labeled 1, 2, 3, 4, 5. So if I cancel a class, then, you know, we just continue with next lecture on the next class, and it's up to you to keep in mind which number we're at. So today we did number 5, right? meaning next time we meet, we do number 6. So having a non-finite m violates the assumed continuity. Yes, if m is infinite and you extract a subsequence where the function values goes to infinity, it violates the continuity at the limit point of that sequence. All right, next question. When you solve limits in several variables, you often replace y with some function depending on x. Why do you do that? How do you know which functions to choose? And when do you know when you're done and can say the limit exists? Emily, I'm sorry, this question is too loose. It has to be brought in the context of an actual exercise. But I understand what you're going for, and the question points out the difficulty with limits, which is one, if you want to use the definition to prove that the limit exists, you need to estimate your function and the difference from the function value to the limit value. And there are just so many ways of doing that. So, in high school, when you did math, there was always like they taught you a method to solve something. And then every exercise was like you apply the method. So you're basically just mechanically following a scheme. Here, it's not like that. So if you want to prove that something is continuous at a certain point, there's just so many ways of doing the necessary estimates, and neither of them is right or wrong. I mean, all of them are right as long as the estimates are done correctly. Yeah, so that's, I guess, what I can say a bit loosely about that topic. But I recommend you to take a concrete question where this swap from x to y that confuses you happens. And now we're out of time, so ask Daniela about it, or even if you can tell me, look at example blah 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 in lecture notes so and so, I can continue discussing it here now because I'm not in a hurry.
Marcus?
Yeah.
Yeah, I have a question about the limits when you're in two variables. Instead of approaching it as a disk, could it be possible to approach it like component wise and then choose the bigger n? So like first you would approach it on, say, the x-axis,
Yeah.
and then do another limit where you just approach it on the y-axis and choose the biggest n between those two, instead of approaching it as a disk.
I don't fully understand that question. I mean, so the limit in two variables, a sequence has a limit y. If you put a disk around y with any radius and prove that for large enough n, you're inside of that disk. Now, if instead of a disk, you take like a box,
Yeah.
you get the same thing, right? So these are equivalent definitions, if you know. And the box is closer to what you're saying. So a theorem would be that a sequence has a limit y if and only if the first coordinate converges to y1, second coordinate converges to y2, and if there are more variables, you go like that.
Yeah, that's kind of the idea.
Yes, so this is a theorem, because basically how you visualize this is like if you have a, I mean, if you know that the first variable is within epsilon of the limit point, and the second variable is within epsilon of your limit point, right? Aha, say what you're getting at there. If I know that x and 1, so the first coordinate minus y1 is less than epsilon for all n bigger than n1, and I know that xn comma 2 minus y2 is less than epsilon for all n bigger than n2. Yeah, just hold on, guys. Wait outside, please. So, what does this mean? It means that here's y1, here's y2, here's the point, and the first one says that, okay, I'm within this, so here's plus minus epsilon from y1, and then I have a plus minus epsilon here. So basically, you said take the maximum of the n, so if I put big N to be max N1, N2, what I've shown now, or what I know then, is that this should be a square around y1. That I'm inside the square with center y1, y2, and side length 2 epsilon, right? So this is what happens when each coordinate converges separately. So then, of course, I can inscribe this in a circle with some radius, which I guess actually square root of 2 epsilon radius. And similarly, any box like that, I can put a small circle inside it. So like that, it's easy to see that it doesn't matter if you use the definition of the limit in several variables that relies on disks, or you talk about convergence component-wise, which is somehow talking about boxes. Because at the end of the day, either you have a small box around your limit point or a small disk around your limit point, and you force your sequence inside that box or inside that disk.
Yeah, okay, thank you. That answers the question.
Right, so now yeah, you're welcome. Okay, so lecture is over. I'm just gonna chat a bit more about one question here with Emily. And you say pick page 680, but I don't have the book here. Sorry. Yeah, well, I think we're getting. Try to ask Daniel, Emily. And if you don't get an answer from him, send me a private. Send me an email, and I will get back to you about this one. I'll try to bring the book in the future. Okay, folks, that's all for today. Over and out.